Hey everybody, this is Larry. This is me attempting day 17 of the Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem. Today's problem is going to be 847. Shortest path visiting all nodes. This seems like a shortest path problem. It is the name. Let's take a look. You're given an undirected connected graph of n nodes labeled from 0 to n-1. You're given an array graph where graph survivor is a list of all nodes connected with node I by an edge. Return the length of the shortest path that visit every node. Oh, okay, that is actually not the path that, or not the problem that I was going. You may start and stop at any node. You may revisit nodes multiple times, and you may reuse edges. Okay, so you have a graph. I thought it would be a little bit maybe interesting, but n is going to be equal to 12, and n is equal to 12 means that there are probably some 12 factorial is a little bit too slow, but n times 2 to the n, which is 12 times 2 to the 12, will be fast enough. So something like that, some sort of bitmask dynamic programming is what it hints at. I actually thought that there may be a better thing for it. Oh wait, did I misunderstand? Oh, it's visiting all nodes, so this is okay. Well, I think I misread this due to this problem or this thing. I think you have to visit every edge. In that case, it'll be some sort of Eulerian path or Eulerian cycle or something like this. And the thing with that one is, it is polynomial, right? But I guess we did something similar recently. But if it's visit all nodes, then it's a little bit different because now basically this is depending on how the problem is structured. It's either TSP, travel salesperson, or Hamiltonian path, Hamiltonian cycle. Well, it doesn't have to be in cycle in this case, but yeah, something like that. But the common part about all those things, and I just misread it a little bit, is that they're all NP plus, right? I say NP plus just because I'm a little bit lazy. I always forget where hem path is in NP or NP complete. For me, it doesn't really matter, or whether it is. Yeah, I always forget whether it's an NP complete or whatever. But I mean, it's exponential, I think is the point that I'm trying to make, which of course is going to be hard enough. And what that means is that there are two things, right, in general for NP problems. One is, once the ability to recognize an NP problem means that you stop looking for, a polynomial solution, right? Or if you do, then maybe you'll be well famous. Or, maybe there's some constraints that you can exploit that makes it not NP. Maybe there's like like one random rule in the problem that is like, oh, it's this, but you can do this one thing. And then you're like, okay, well, this one thing changes everything. And it's not an NP anymore, right? And then in real life, what you would end up actually doing is couple of things. There are a lot of things you can do, but I think there are a couple of things that are off my head. One is just looking for an approximation algorithm. So in that case, you'll try to find an algorithm that you can maybe prove is within certain percentage of the optimal, especially in this particular in TSP, like there is such a thing, of course. Or you may look at the try to figure out the additional constraints or looking for properties within a certain input that you can exploit, right? Like maybe for whatever reason, like you realize that 80% of your input is bipartite or something like this, right? I don't know. And then in that case, you can solve 80% of your things, like your real life data set may be useful. Or maybe you notice that the graph is planar or something like this, right? Some sort of property that you can play around with and kind of make a special case for, and maybe you can solve them in a piecewise meal or something like this. In any case, that's a lot of talk, but yeah, knowing that this is an NP means that we don't really try to find something better than NP. Of course, in this case, you can do dynamic programming, and given that 2 to the n, or n times 2 to the n, where n is 12 is fast enough, we can kind of just get started. And of course, the way that we're going to do this is with What's it called? Bitmask dynamic programming. Bitmask dynamic programming is such a fancy word. If you haven't done bitmask before, I'll do a very brief intro, but I think it's very intimidating. It can be intimidating to say and see if you read all these like funky symbols for the first time, but it's not that bad. I promise you. Yeah, okay, it's understandable. I believe in you. But yeah. So let's say we want to write a brute force, right? How would we kind of write this? So the way that I would just write it is like the 12 factorial way, right? Like go from 0, then 1, then 0, 2, like, just all the permutations, right? So yeah, so maybe we can do something like, what are we supposed to return? The length of the shortest path. Okay. A couple of ways you can do it, but I think like for start in range of n, maybe best is equal to some infinity, right? So best is equal to min, best, and then calculate from the start, and then return best, right? Something like this. And maybe, we were writing before, so maybe we have a scene thing, where, scene is equal to force times n, or something like this, right? I'm going to write it the brute force way a little bit first. I mean, just to kind of, you could skip ahead if you already think you already know what I'm going to do, but yeah. So then now to the current node, and then you have the scene array, and then the idea is pretty straightforward. It should be right. It's structured like what did I do? Graphs of current. So for v in this, that's the next node. We can, we can calculate, same things, best is equal to infinity, and then we turn it, we can do a calculate on v, and then scene, right? And then maybe like scene of v is equal to true, and this is scene is equal to false, something like this, and then best is equal to min, best, this plus 1 because we took an edge or something like this, right? So there are a couple of ways you can write this as well, or even optimize even this. But that's the really straight core part of writing it in a brute force kind of way, right? And it's not quite right because there's no base case, and you can kind of go back and forth. I am aware of these things, but that's kind of like the most basic way to kind of write, just like a brute force, right? Like we say, brute force, this is a brute force, and this would never terminate just because you can go back and forth. And also we don't have a base case. So base case is something like all scene is I guess that's actually good enough. With all scene, then we return 0, right? Meaning that we've visited every node, then we return 0. One, it'll never finish. I don't think. Oh well, it'll never even start apparently. But even assuming all the syntax is correct, it'll never finish, right? Actually, a little surprised, but not that surprised, because yeah, probably only 1,000. But yeah, it goes is too much of a recursion depth, and if you let it, it'll probably even go even more, and you'll always run out of stack space eventually. Yeah, okay. First thing to note, what are we doing, right? First optimization step. One thing that we can do here is, we go back and forth from nodes we already seen. So how do we skip nodes that we've seen before? Well, if we want to skip the nodes that we've seen before, then we can just do something like this, right? If not seen of v, then we do this. But this is not going to work either, because, or by itself, it doesn't work, because like we have example 1 where you want the 0 to go to 2 and then back up, right? There's no path, or at least the way that we've written it, there's no path going from 1, 0, and then 2, and then 3 directly, or at least not as given. So maybe one thing that you can do, and there are different ways to tackle this, but the way that I'm going to tackle this problem is just write the shortest path thing, right? So yeah, so what I mean is that now I'm creating all pair shortest path. There's only n, there's only 12, or n is equal to 12 number of nodes. So 12 squares, n squared, that's enough to do anything really. So yeah, so let's get to that, right? So let's just say infinity times n for right? Yeah, and maybe you can do something with the base case like d of I is equal to 0, something like this. And then now we can also go through the list. So for I in range of n, I guess we already have that loop, right? For v in graph of I, d of iv is equal to d of vi is equal to 1, right? I think it shouldn't matter whether we do it. I mean, it's a symmetric thing, right? So now we have the one distance away thing, and here I'm just gonna, there are a couple of ways you can do the all pairs shortest path. I'm just gonna write it with Floyd-Warsha's algorithm, right? Yeah, for range of n, for I in range of n, d of ij is equal to min of d of ij, d of I k plus d of kj. I'm not gonna go over this part too much, to be frank. There are different ways to do it. Cannot type. Definitely look that up and Google it up or whatever as you need. So then now we can actually get this to be a little bit correct, in that instead of now going from current to v, we can just do d of current to v, right? And and now we don't have to do dupes, so that's good, right? Maybe in theory anyway. Yeah, I actually don't know why this is return infinity. I think this should, this will still time out for n is equal to 12, but it should be okay for these inputs, to be frank. So I'm trying to think, what did I miss something silly? Which is probably possible. And yeah, well, I didn't do scene of start is equal to true. So I guess that's one thing, but where am I doing this? I mean, I know that this is infinity, but did I mess something up? I mean, clearly, but okay. So this array is fine. But then why does this work? Huh? I did forget this part though, but. What is going on? This is never hit. Did I maybe misunderstand? It should always be possible. Oh! I'm being dumb. Sorry. I did. Okay. I made a modification for this, but that also means that this is no longer true because these are only one distance away edges. So now we have to do something. We have to change this to going from 0 to n altogether. Okay, there we go. And yeah, and like I said, this is going to be n factorial, which is fine up to like 7 or 8 or something like this, right? Maybe even, I don't remember what the number is, but 12 is getting it a little bit tight. What is 12 factorial? 12 factorial is 479 million. Actually, maybe in some languages it'll be okay, maybe. I don't even think that's true, but either way. Now we have to do something called, well, I mean, and this is, at this point, we have to do some memoization. Note that every time we record this, if we give it the same input, we expect the same output, and that is basically the only condition for memoization, really. No side effects, no weird things, and that will allow us to do it. So how do we memorize this? Well, current can go from 0 to n, so that part is easy, 0 to n minus 1. Scene is just basically a Boolean array of, Boolean array n values, right? And so this is where the bitmask stuff comes in. You can kind of see how I did it with the Boolean array, but what is a Boolean array? Well, Boolean array, you can think of it as like just ft, like false and true values. And if you kind of convert these false true values to 0 and 1s, so f for 0, t is 1, so you could kind of you could convert them to binary values, and now instead of an array of bits, you can just condense them into one number, and that's basically a bit mask, right? Every other operation we'll do together, but this is basically the logic of what it looks like, and yeah, and because of this, and now we can think about it with n values, how many possible distinct values there are. Well, each one of them could have 2 values, and there's n of them, so it's 2 times 2 times 2 dot dot dot, which is also 2 to the n. So that means that total number of inputs is O of n times 2 to the n. And each input takes O of n times, at least the way that we did it. So that means that total is actually going to be, total time is going to be O of n squared times 2 to the n. So I was off by n actually. Whoops. And total space though would be n times 2 to the n, right? That's pretty much the idea, but just to kind of make it a little bit compact, and you can actually, at least in Python, you could actually use like a frozen array or something like this. Maybe I made that up, but you could definitely memorize on this already if you really want to. You have to be a little bit careful about arrays, because you want to memorize not the memory address, which may be the thing with cache. I don't know. So yeah. And for this particular video, I'm going to just try something funky and kind of just keep it the same, and then just change the memoization function, right? So concurrent and the scene, fine. Like hopefully this is understandable so far. This is very brute force, top down kind of thing, right? And then now we just have to basically has same thing that I always do, at least on these videos, just to kind of just to kind of visualize a little bit better both the space and the usage, right? So here now, if all scene we return 0, that's fine. Otherwise, let's see, what do we want to do? Right. Otherwise, we have to see if has cache, right, of current and scene. But of course, scene cannot, scene is an array, it's not a number, so we just have to convert it to a binary number, right? So yeah, maybe we have a helper function, right, or something like this, right? And maybe we store it so I don't keep calling it, right? Maybe BC for binary. And that's pretty much it. Of course, we have to write the to-binary function, and you can write the to-binary function in a number of ways as long as you're consistent about it, right? So, for example, now we can say, right, for v in scene, current we shift by 1, or so we multiply by 2, and then we add it. If v is true, then we add it by 1 or something like this, right? And that's pretty much it, really. Yeah, I'm gonna give us. I'm gonna give some. I mean, the idea is gonna be right. It's just I'm worried a little bit about typos and such. But let's just give it some it, and we could fix it. Yeah, and that's pretty much it. 1265-day streak. Yeah, I mean, the timing is a little bit rough, but that's fine. Yeah, I think with these kind of problems, hopefully the way that I illustrated, maybe another way of doing bitmask DP, right, to show what bitmask DP is. It doesn't have to be intimidating, but yeah. that's all I have for this one. I think one thing I would also say is that over the years, if you have been following my channel or server or whatever, and you see me do bitmask DP, I've kind of done it in a number of different ways, and I think that's, and I don't know, I don't if it sounds like a brag, you could skip it. It's not really meant to be. But what I want to showcase is not even just like me bragging, but or me saying that like this is the kind of understanding that I always try to teach is not like memorizing code or memorizing, bitmask DP and be like, oh yeah, it's bitmask DP. Always do it this other right? Like it's about different, ways of visualization, different ways of coding. There are a lot of different things, and yeah, certain ways will be more optimal, but getting to that point and being able to get that point and really have the understanding to kind of make changes along the way is going to be the real difference when it comes to tougher problems that are a little bit more difficult. This one's okay though, so yeah. But yeah, anyway, that's all I have for this one. That's all I have for this problem. Let me know what you think. If you're doing the contest in an hour and a half or so, good luck. Wish me good luck. But yeah, stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye bye.